Okay, hello everyone. In our last class, we have been discussed introduction to eyepiece. Eyepiece used in every optical instruments like microscope, telescope, etc. If we are going to consider the microscope here, the eyepiece located here, objective lens located here, the specimen or object located here. Why it is called as the eyepiece? Because it is nearer to viewer or eye. Okay, in market we can get various type of eyepiece: Huygens eyepiece, Ramsden eyepiece, Kellner, RKE, orthoscopic, etc. This is the physical appearance of an eyepiece. Overall, we found eyepiece is the combination of field lens and eye lens. In detail, we have been discussed in a last class about introduction part of the eyepiece. In this class, we are going to discuss construction and working of Ramsden eyepiece and its location of cardinal points with an important numerical. Okay, so let us start. Here, this figure represents the construction of Ramsden eyepiece. Before we are going to discuss its working, first we have to know who was the Ramsden. Here, J.C. Ramsden was a British mathematician and astronomical scientific instrument maker who invented this eyepiece in around 1782, and this eyepiece in general used in telescope. Okay, now we are going to go for the construction part. Here, it consists of two plano-convex lenses made up of same material, has been kept as face to face separated by a distance 2f/3. Here, two plano-convex lenses separated by a distance 2f/3, convex side faced with each other. Here, focal length of each plano-convex lens is your f. Focal length of this lens is your f. This lens is also f. The lens which is towards objective lens is called field lens, whereas the lens which is towards observer is called as eye lens. So this lens towards objective lens is called field lens. This lens is towards observer or eye is called eye lens. Here, one note I written. You should remember that whenever we are going to design a eyepiece, we should minimize the aberration of that eyepiece. Different type of aberrations are there: spherical aberration, chromatic aberration. So how to minimize? We should minimize the aberrations. Okay, so for this case, to minimize the aberration, the separation of two lenses having the focal length f1 and f2 should be equal to f1 plus f2 by 2. So if we are going to think a eyepiece, to minimize the aberration, this is the first step that we have to follow. Suppose this lens having the focal length is your f1, this length is your f2, and separation should be f1 plus f2 by 2. So here you can see the focal length of each lens is your f. So separation should be how much? F plus f by 2. That means f. But here you can see the separation between two lenses is your 2f/3, not f. Why? Practically it has been found that, here I written, but it is found that practically it is found that in case of Ramsden eyepiece, the most suitable separation between two plano-convex lenses is your 2f/3. See, theoretically we can minimize the aberration by considering this step. That means we have to separate the two lenses by a distance f1 plus f2 by 2. This is nothing but theoretically, but practically it is found that for Ramsden eyepiece, the aberrations minimized when they placed with a separation 2f/3. So in the figure you can find the two lenses separated by a distance 2f/3. Okay, now we are going to go for the working. Here, I1, this one, I1 is the image produced by the objective lens by converging the beam coming from object. This I1 will treated as object for field lens. I2 is the image produced by the field lens and viewed by the lens. The I2 will be formed at the focal length of the eye lens. Hence, ray coming from I2 after passed through eye lens emerged parallel with each other as shown in figure. Here I am going to explain. This I1 is nothing but your image formed by the objective lens. First you see this figure. Consider this figure here. This is the telescope. Okay, because we know that the Ramsden eyepiece is used in the telescope. Here in the telescope, through this side where eyepiece is present, here eyepiece is present in this telescope. Here it is written. Here objective lens is present. Through this telescope, suppose you are viewing this long distance tree. Here you can see in front of objective lens, object is there. So if we are going to consider this figure, this is your objective lens and this is the eyepiece, combination of two plano-convex lens, and this eyepiece is present here in this instrument here. Okay, here. So this eyepiece, that means two plano-convex lens separated by a distance 2f/3 like this. Okay, 2f/3. So this is your eyepiece present here. In front of this field lens, objective lens is there. Objective lens here in front of the field lens. In front of objective lens, objective there. Okay, so here what is the working of this objective lens? The objective lens collects the light from the object and it will create an image in front of field lens. This I1 is nothing but image created by this objective lens in front of field lens, and this I1 will act as object for this field lens, which will viewed by this eye lens or viewer through this eye lens. Got it? Same thing I have been written over here. I1 is the image produced by the objective lens, by this objective lens, by converging the beam coming from the object. This I1 will treated as object for the field lens. Here this is the field lens, and this system, combination of two plano-convex lens, is your eyepiece. Here this combination of lens is called as the so-called optical system itself, you can say. And in front of field lens, objective lens is there. In front of objective lens, somewhere, if this is a telescope, then object will be at the farther distance. Okay, if telescope, if it will a Huygens eyepiece, that means it will a microscope, so object will be placed nearer to the objective lens. But in case of telescope, particularly for the Ramsden eyepiece, the object will be at the farther distance because it is a telescope. Got it? This eye here, I2 will be treated, I1 is treated as object for the field lens. Now, how I2 formed? I2 is the image produced by the field lens. This is the I2 magnified one. I2 is the magnified image produced by the field lens and viewed by the eye lens. The I2 will be formed at the focal length of the eye lens. Here, this I2 will be formed at the focal length of the eye lens. Hence, ray coming from I2 after passed through eye lens emerged parallel with each other. Here, this I2 produced at the focal length of this eye lens. So, what is the focal length of the eye lens? Is f. So, from this eye lens, that means from the center of the eye lens towards left, here you can see what is the distance? F distance. After f distance, this I2 is produced. That means I2 produced at the focal length of this eye lens. So whatever the ray coming from this I2 after passed through this eye lens, obviously they will be parallel with each other. You just recall, suppose this is your simple lens, okay, and this is the focal point, and if the ray will be coming out from this is the focal point. first focal point. If the ray coming out from this focal point, after refraction through this lens, it will be parallel with the principal axis. Okay, so from this eye to whatever the ray will be coming out after passing through this eye lens, the rays passing through the eye lens emerged parallel with each other. Okay. Now we are going to calculate the location of cardinal points of this Ramsden eyepiece. Here I written the heading as location of cardinal points by using system of matrix SM of this Ramsden eyepiece. Before I am going to calculate the cardinal points, first I am going to recall you about the lecture number 13. In lecture number 13, we have been discussed in detail about equivalent focal length of two thin lenses separated by a distance t, and also we have been evaluated the cardinal points of this optical system. Here optical system is nothing but combination of two thin lenses. Here in this box, in this dotted box, two thin lenses separated by a distance t. Here lens L1, L2, L1 having the focal length f1, L2 having the focal length f2, and we found the system matrix of this optical system was 1 minus t by f1 t. Here t is the separation between the two thin lenses, f1 f2 are the corresponding focal lengths. 1 minus t by f1 t minus 1 by f1 minus 1 by f2 plus t by f2 f1 or f1 f2, 1 minus t by f2, equation number 1. This is in general expression if we are going to consider two thin lenses separated by a distance. This system matrix I am going to use for Ramsden eyepiece, because in case of Ramsden eyepiece, two plano-convex thin plano-convex lenses separated by a distance 2f by 3 and each having the focal length is your f. Okay, same thing I have been written over here. In general, we know in the system of matrix, the system of matrix of combination of two thin lenses separated by a distance t, what we found, same matrix I have been written over here in general. Let this is your equation number 1. But in this case, for Ramsden eyepiece, f1 f2, f1 is the focal length of field lens, f2 focal length of eye lens, both are same. Small f I have been considered, small f, and t separation between them is your 2f by 3. So these values here I substituted in your equation number 1. We can found this one, this matrix. Here you can see 1 minus, instead of t, 2f by 3 substituted, instead of f1 substituted as f, instead of t here 2f by 3, f1 f2 f, here f1 f2 substituted by f, t 2f by 3, here t by f2 substituted by 2f by 3 and f. You just simplify, you can found, do it by rough, you can found this value is nothing but your 1 by 3. Here f got cancel, then 1 minus 2 by 3 is nothing but 3 minus 2 by 3 minus 2 by 3 is nothing but 1 by 3, and this is your 2f by 3. You just simplify this one, you can found this value minus 4 by 3f, this value will be 1 by 3. Let this is your equation number 1. Now if you want to verify this matrix, you can also verify. See, what is the need of the verification? We know that the system matrix of an optical system will be acceptable if and only if the determinant of the system matrix is unity. So if this is the system matrix of this Ramsden eyepiece acceptable, at that time it will acceptable if the determinant will be 1. You just calculate rough, you can found the value will be 1. Okay, you just do it rough, take the determinant of this matrix, you can found 1. So this is the system matrix of this Ramsden eyepiece. Okay, but in general the system matrix of an optical system, of any optical system, is represented by what? A, B, C, D. These are the 4 elements in general. Let this is your equation number 3. Now you just compare equation number 2. That means this matrix and 3, this matrix. We get A equal to 1 by 3, B equal to 2f by 3, C equal to minus 4f by minus 4 by 3f minus 4 by 3f, D equal to 1 by 3. Okay, so here we found A, B, C, D values. By using these values, we can evaluate the cardinal points of this Ramsden eyepiece. Okay, here you can see one by one we are going to calculate. Yes, before we are going to calculate the cardinal points of this Ramsden eyepiece, again I am going to recall you about lecture number 13. I suggest you first you watch this lecture number 13, where we discussed in detail about calculation of cardinal points of combination of two thin lenses. Okay, in that lecture we found these are the cardinal points: x1, x2, focal points, location of focal points from input and output planes, r1, r2, location of principal points from input and output planes, z1, z2 belongs to nodal points. Here small f1 and f2 belongs to focal points and focal lengths of this optical instrument, optical system. Here optical system means combination of two lenses. Okay, so I suggest you go through this lecture first before you are going to watch the Ramsden eyepiece. Now we are going to use these equations to evaluate the cardinal points in our case. Okay, so I again suggest that you just remember these equations, most important for solving the numerical. Okay, now we are going to calculate the cardinal points, location of cardinal points one by one. First we are going to calculate the location of first and second focal points. Here we found A, B, C, D values are 1 by 3, 2f by 3, minus 4f by 3f, D equal to 1 by 3. Same values I written over here in this slide. First we have to evaluate the location of first and second focal points. Okay, here previously it has been found that, here why I written previously, because in this lecture we evaluated the cardinal points by considering two thin lenses separated by a distance. If I am going to compare in our case, here also two thin lenses separated by a distance. So these equations directly we are going to use to evaluate the cardinal points of the Ramsden eyepiece. Okay, only for that I written previously it has been found that the location of first focal point f1 from input plane can be evaluated by using the equation x1 equal to d by c. Here you can see, here x1 is nothing but focal point, first focal point, location of first focal point from input plane. Same thing I have been written, and the value of x1 is your what, d by c. D by c I written. Okay, x1 equal to d by c. D value is your 1 by 3, c value minus 4 by 3f. Here I substituted, and we can found x1 equal to minus f by 4, minus f by 4. So here we found x1 value is a negative. So negative means we have to move towards left. Hence from the above result it is found that first focal point f1, here f1 means here first focal point, focal point, and your input plane is this one, this dotted line is your input plane, right? From input plane we have to move left how much distance, f by 4 distance. Same thing I have been written over here. Hence from the above result it is found that first focal point f1, this one f1, is located left to the input plane by a distance f by 4, by a distance f by 4. Okay, okay, then we are going to calculate second focal point. Same thing I written previously it has been found that the location of second focal point f2 from output plane can be evaluated by using the equation x2 equal to minus a by c. Here you can see x2 equal to minus a by c. So here a value 1 by 3, c value minus 4 by 3f. Just substitute these two values calculate, you can found the value is your f/4 but positive. So if positive means we have to move towards right. Hence, from above result, it is found that second focal point F2 is located right to the output plane by a distance how much f/4. So where is the output plane? Here is the output plane. This is your output plane. From this output plane, we have to move how much distance? f/4 distance. This one, this much distance, and we can found the second focal point. Okay. Now we are going to evaluate the location of first and second principal points. Previously it has been found that the location of the first principal point from the input plane can be evaluated by using the equation r1 equal to d minus 1 by c. See, this r1 represents the location of a principal points, first principal point from input plane. You can see here r1 is d minus 1 by c from input plane, r2 is your 1 minus a by c from output plane. Same equation I am going here I used, because both the cases are same. They are also two thin lenses. Here also two thin lenses separated by a distance. R1 equal to d minus 1 by c. Here d value is your 1 by 3 minus 1 by c. C is your minus 4 by 3f. After calculation, you can found f by 2. So here by 2 we found positive value. That means we have to move towards right to the input plane. From the above result, it is found that first principal point P1 is located right to the input plane, So this is your input plane. So we have to move how much distance? f/2 distance. f/2 distance. Then we can found the location of first principal point by a distance f/2. Got it? f/2. Now we are going to evaluate our second principal point. Location of second principal point. Previously it has been found that same language I have been used. Okay, here in your exam you can reduce these writings. Okay, here I written these writings, you can reduce in your exam, but now you just write in your note. Previously it has been found that the location of second principal point P2 from output plane can be evaluated by using the equation R2 equal to 1 minus a by c. Here a value is nothing but your 1 by 3, c value minus 4 by 3f. Just substitute these values and you can found the value is your minus f/2. So here we found negative value, means we have to move left from the output plane. So this is the output plane. From this point we have to move how much distance? f/2. Then we can found location of second principal point. So this is the f/2 moved towards left this much distance. This is the location of second principal point. Got it? Okay, same thing I have written. Hence from the above result it is found that second principal point P2 is located left to the output plane by distance f/2. Now location of first and second nodal points. Here you can see mu I and mu O, refractive index of input and output space is same. If it is so, then we know that R1 will be equal to Z1. Here R1 equal to D minus 1 by C. Here also D minus 1 by C. Here 1 minus A by C. Here 1 minus A by C. That means both principal points, first and second principal points and first and second nodal points will be coincided with each other. Okay, same thing I have been written over here. Location of first and second nodal points is nothing but for mu I equal to mu O, R1 equal to Z1, R2 equal to Z2. That means conjugate nodal points are to be coincided with conjugate principal points. So these P2 P1 conjugate principal points and N2 N1 conjugate nodal points both are located at the same position. Okay, that means both are coincided with each other. Now we are going to evaluate equivalent focal length. This is somewhat important point. You just carefully watch. Equivalent focal length of of the Ramsden eyepiece. Equivalent focal length of the Ramsden eyepiece. Here I have to write first of the Ramsden eyepiece. Just wait. of Ramsden eyepiece. Most important, this is most important point, carefully you just watch. Previously it has been found that F equivalent is equal to minus 1 by C minus 1 by C. That means we have to follow our lecture number 13. This is your lecture number 13. We found F equivalent equal to minus 1 by C. Here, if you are going to compare this F equivalent with F2, both are same. Here minus 1 by C, here also minus 1 by C. Carefully you just watch and listen. Here F2 value is nothing but your minus 1 by C. Here F2 represents the equivalent focal length, not the focal length of individual lens, not the focal length of the individual lens. Okay. From initial itself, you can follow the lecture number 10 where we discuss the cardinal points of a optical system in general. And from that video, we consider F1, F2 as the equivalent focal length of a optical system. Okay, so here F2 represents the equivalent focal length of this optical system. Here in this case, optical system is your combination of two thin lenses, and the value is your how much? 1 minus 1 by C. We are going to consider this value. This value is your C from the system of matrix. So here F equivalent is minus 1 by C, or we can say second equivalent focal point, and corresponding length is your second equivalent focal length F2. Here F1 means F1 is a first equivalent focal point and corresponding focal length. Okay, both are opposite sign. This is your minus, this is your plus. Okay, same thing I have been written over there. Here previously it has been found that F equivalent is nothing but minus 1 by C. As I discussed that F equivalent is nothing but F2. Here capital F2 is nothing but your position of equivalent focal point of this optical system. Here optical system is nothing but your Ramsden eyepiece. This is your optical system. Here input plane to output plane. Here input plane to output plane. The system is called as the optical system, or the so-called Ramsden eyepiece, right? Here capital F2 located at here, capital F1 located at here. So here capital F2 means equivalent focal point, or you can say second equivalent focal point. This F1 here, this F1 is your this one. Capital F1 is your first equivalent focal point, and its corresponding lengths from the from principal points will be called as your equivalent focal lengths. Okay, so here F2, if I'm going to consider F2, capital F2 is nothing but F equivalent, or we can say its value is equal to nothing but small f2, as per our uh, lecture number 13. Okay, so here small f2 is equal to capital F2, and in general it is called as F equivalent. Suppose somebody will be asked the equivalent focal length of the Ramsden eyepiece, that means this F2. F1, if I'm going to consider F1 is nothing but this small f1 value is your 1 by C. Here minus 1 by C. That means magnitude will be same, but the sign is different. Here 3 by 4, here minus 3 by 4. So here this capital F1, which will be calculated from which will be evaluated by using this equation, is represents the fast equivalent focal point located left to the first principal point, and its corresponding length will be called as first equivalent focal length. In general, this is called as this capital F2, which evaluated by using this equation, that is your F2, small f2 equal to 1 by C, is nothing but called as your equivalent focal length of an optical system. So what about this one? This is present, this focal point and this corresponding focal length also present for an optical system, but in general equivalent focal length for an optical system is nothing but this one. So most of the book followed this language. Okay, don't be confused. So this f1 is located for the Ramsden eyepiece is located at here, and this this F2 located at here, this F1 located left to the principal point, first principal point. How much distance? Here I shown also. Here I shown in the figure. How much distance? As it is negative value, so it, it will be located left to the principal point P1, first principal point P1. How much distance? 3f/4. Here, from first principal point, we have to move 3f/4 distance. Then we can found first focal point. Here, f2 value is your 3f/4, but positive. That means from P2, we have to move here. We have to move 3f/4 distance towards right, and we can reach at the F2, second focal point. In general, F2 is called as the equivalent focal length of the optical system, of any optical system. Most of the books, they are writing in this language. And here you can see F1 magnitude is equal to small f1 magnitude, and also this one equal to F2 magnitude equal to small f2 magnitude, because both are 3/4, 3/4. Okay. Here, F1, F2 are called first and second equivalent focal points, are located left and right to the first and second principal points respectively. The corresponding magnitudes, this one, are called equivalent focal lengths of this optical system, Ramsden eyepiece. What I told, most important, I given star itself. In general, F2 is called equivalent focal length, and its magnitude, this one, is called equivalent focal length of an optical system. You just remember these things in your mind. Okay. Now we are going to solve a numerical belongs to Ramsden eyepiece. Here, this is the question. In the question, it is given that focal lengths of each lenses of Ramsden eyepiece 10 cm. Find the position of cardinal points and show them in the diagram. If this question will ask in your exam, it will ask for 4 to 5 mark. Watch carefully and practice it. Given f1 equal to f2, that means here field length and eye length, focal length is your 10 centimeter. So let f is your 10 centimeter. Separation distance, this should be t. Okay, will be how much? 2f/3. In case of Ramsden eyepiece, always the separation will is your how much? 2f/3. Here 2f/3 is the separation. Now we are going to use the system of matrix. This is also t. We know that the system of matrix of two thin lenses separated by a distance t is nothing but 1 minus t by f1, t minus 1 by f1 minus 1 by f2 plus, in general, that we know. Instead of t, how much we have to substitute? 2f/3. Instead of f1 and f2, we have to substitute as value f. Okay, you just substitute first. So instead of t, 2f/3. Instead of f1, f. Instead of t, 2f/3. Instead of f1 and f2, f. Here 2f/3 and f. As per the question, f given that 10 centimeter. Okay, and you just substitute this value, f value, here. This is your how much? F got cancelled. 1 minus 2/3 is nothing but 1/3. Here this element also 1/3. Here 2f, f is nothing but 10, value 10 given in the question. So 2 into 10/3. Here you just calculate this much value. You can found minus 4/3 into 10. So this is 1/3 written as such. This will be 20/3, and this will be minus 4/30, and this is fourth element is your 1/3. Let this is your equation number 2. Now consider the general system of matrix of any optical system, that is your A, B, C, D. Comparing equation number 2 and 3, we can found A, B, C, D values. 1/3, 20/3, minus 40/3, and D is your 1/3. Okay. Here this is your T. Okay, I'll correct it after that. Here we found A, B, C, D values. I written over here. Now we are going to consider our lecture number 13. In lecture number 13, considering two thin lenses separated by a distance, uh, the location of cardinal points can be evaluated by using these equations: x1, x2, r1, r2, z1, z2, f1 and f2. See, this f1, f2 is not the focal length of field lengths and eye lengths. This f1 represents the equivalent focal length of this is optical system. This is first and this is second equivalent focal length of the optical system. So here, by using these values a, b, c, d and these equations, we can evaluate the cardinal points, or we can straight evaluate. Here we found the cardinal points equations for the Ramsden eyepiece. Here x1 is your minus f by 4, x2 is your f by 4, r1 is equal to f by 2, r2 is your minus f by 2, and f equivalent is your 3f by 4. Same thing I have been written over here. This. So if I'm going to consider x1 minus f by 4, f given that 10 minus 10 by 4 minus 2f by 4, same result also we can get by considering this equation number 5. Here in equation number 5, d by c, d is your 1 by 3, c is your 20 by 3, sorry, c is your minus 4 by 30, minus 4 by 30. So this will be how much? Minus 30 by 4 into 3, that is your minus 10 by 4, minus 10 by 4, that we can get also minus 2.5 centimeter. x2 value, if I'm going to consider for Ramsden eyepiece, f by 4 we found, and the value is if I'm going to calculate by substituting f equal 10, 2.5. r1 is nothing but your f by 2, f is your 10, we can found 5. r2 minus f by 2, we can found the value is your minus 5. f equivalent 3f by 4. If by substituting f value and after calculation, we can found 7.5 centimeter. Here if I'm going to consider f2 minus 1 by c, here if I'm going to consider f, same answer also we can get minus of 1 by c value is your minus 4 by 30. Okay, 4 by 30 minus plus 30 by 4, here 30 by 4, same answer 7.5 centimeter also we can get. Here f equivalent is nothing but minus 1 by c, that means f equivalent f2 already we have been discussed, right? Now we are going to locate these locate the cardinal points by using these values, right? This x1 is nothing but what? x1 is the location of a first focal point from input plane. Here in detail I have been discussed. X1, same thing I have been written, same values, x1, x2 minus 2.5, r1 5, r2 minus 5, f equivalent 7.5. I written the same values, x1, x2. Here x1 is the location of a first focal point to the left. Why left? Why left? Because it is minus of the input plane, and x2 is the location of second focal point f2 to the right. Why right? Because this is plus value of the output plane. So here 2.5 we have to move here. This is the Ramsden eyepiece, in general. This is the Ramsden eyepiece as per the question. Okay, as per the question. So how much distance we have to move from the input plane to locate the f1? Minus 2.5, or this distance is minus 2.5. That means we have to move towards left from the input plane. How much distance? 2.5. Got it? Likewise, to locate the f2 here, we have to move right to the eye lens or output plane. Clearly I written output plane, right to the output plane. How much distance? 2.5 distance, 2.5 centimeter distance, and we can locate f2. Got it? Now consider r1. r1 is your positive, r2 is your negative. Positive means we have to move right, negative means we have to move left. Here r1 is the location of first principal point to the right, because it is positive, to the right of the input plane. r2 is the second principal point to the left of the output plane, to the left, because it is negative. So here input plane is this one. This one is the input plane. So we have to move how much distance? 5 centimeter distance right to locate the P1. 5 centimeter distance from here, this one, here we have to move how much distance? 5 centimeter. 5 centimeter we can found P1 point, first principal point, this one. Now for the second principal point, what we have to do? We have to move left from the output plane. How much distance? 5 centimeter. This is the output plane. Move towards left 5 centimeter. This distance. This distance is your 5 centimeter. 5 centimeter, or R2 I located. R2 equal to minus 5 centimeter. Minus 5 centimeter from output plane towards left. Okay. Now F2, or the so-called small F2 or F equivalent, is your 7.5 plus. Here plus 7.5 plus. That means we have to move right to the second principal point. Carefully you just read and remember this point. I suggest you just remember this point. Here F2 represents the location of second equivalent focal point located or situated to the right of second principal point. How much distance? This is the second principal point. Second principal point is your this one. Okay, we have to move 7.5. See, this distance, this to this distance is your 5, this to this distance is your 2.5. Obviously this to this distance your 7.5. This is your so-called location of F2 from second principal point. How much distance we have to move towards right? 7.5 centimeter. Then we can found the location of equivalent focal point, or second equivalent focal point, whatever you can say. Okay. And its length is called as your focal length of this Ramsden eyepiece. Equivalent second focal length. Second equivalent focal length. Here I have to somewhat modify. Second equivalent focal length. Just wait. Second equivalent focal length of this optical system, that is your Ramsden eyepiece. But again I written with star mark. Simply it is called the equivalent focal length. This F2 in general called the equivalent focal length of the optical system. Now what is the importance of this F1? Here F1 value is nothing but 1 by C. 1 by C value, by considering 1 by C, we found minus 7.5 centimeter. That means we have to move left to the first principal point. Here F1 represents the location of first equivalent focal point situated to the left, because it is minus of the first principal point, and its magnitude is called first equivalent. I'm going to modify it. First equivalent focal length. Okay, first equivalent focal length. Here how much distance we have to move? 7.5 from first principal point. This is your first principal point. We have to move 7.5 distance. Then we can found this point, F1 point. Here this point to this point, this distance is your how much? 5 centimeter. Okay, this input plane to F1 distance is your 2.5 centimeter. So 5.5 plus 2.5, 7.5. So from here P1 to F1 distance is your 7.5, and this focal length is called as, and its corresponding magnitude is called as your what? First equivalent focal length of this Ramsden eyepiece. Okay, and for this case, as we know, first and second nodal points are coincided with first and second principal points. So where we have first and second principal points, here first principal point, this is your second principal point, there the nodal points are to be coincided. So this is the location of your first, and this is your second nodal points. Okay. Now we are going to verify for this particular question, whatever the system of matrix, is it acceptable or not. So if I'm going to consider ABCD value, so these are the ABCD value we have been evaluated for this particular question. So corresponding system of matrix will be what? This one. So you just calculate the determinant of this matrix here. 1 by 3 into 1 by 3 minus of minus 4 by 30 into 20 by 3. After calculation, you can found 1. That means this system of matrix acceptable for this Ramsden eyepiece. Okay. Now we are here. I given this question for your assignment. This is a very simple question. You just do by yourself. Equivalent focal length of Ramsden eyepiece given as 6 centimeters. So here equivalent focal length is nothing but what? Equivalent focal length in general, that is your 3f by 4. 3f by 4 given here, 3f by 4 given as 6 centimeter. Okay, find the focal lengths of field lengths and eye lengths. So here f will be how much? 6 into 4 by 3. So here 3 to 8. So here 8 centimeter. That means f we found 8 centimeter. Here f is nothing but focal length of field lengths and eye lengths, because field lengths and eye lengths uh, are same for the Ramsden eyepiece. Okay, this is a simple question I already discussed. You just do it in the rough. So here we completed the construction, working, uh, and location of cardinal points of Ramsden eyepiece, and based upon that we discussed one numerical which is most important for your exam point of view. Okay, here we completed this topic. In our next class we are going to discuss construction and working of Huygens eyepiece and location of its cardinal points with important numerical. Okay, so thank you so much for watching this video. Thank you.